Hello, today we're going to talk about the equations of static equilibrium for a particle. So in static equilibrium, basically what that means again is an object in static equilibrium is an object that's not accelerating. So what does it mean when the acceleration of an object is zero? Well, we've got Newton's second law, F equals ma. If that term a is going to be equal to zero, m times zero is going to be zero, so the force has to be equal to zero. Or really, what this means is the sum of all the forces, the net force acting on the object, is going to be equal to zero. We can also do the same thing with the moment equations. So this is the rotational version of Newton's second law. The moment equals the second moment of inertia times the angular acceleration. That angular acceleration is also going to be equal to zero. If that's true, then the moment equals zero. Really, the sum of all these moments is going to be equal to zero. So these two equations down here are known as the equilibrium equations. So with a particle in equilibrium, a particle is going to be a body where all the mass is concentrated at a single point. In reality, everything has some sort of volume, so particles don't really exist. But what we do have is concurrent force systems. So this is a system where all the forces are going to act through a single point. And when this is true, we treat the system as a particle, even if there is some finite volume. So an example of something that would be a concurrent force system is this traffic light here. We're going to have three forces acting on this traffic light. We've got the weight of the traffic light pointing down. We're going to have the tension on this side, kind of going up at that 15-degree angle. We're going to have a tension going this way, horizontally. So we've got three forces, and they're all acting through this one point right here in the center of this ring. So this would be an example of a concurrent force system, and we treat this whole thing as a particle. So when we have particles in equilibrium, or concurrent force systems, we've got our two equations. Net force is equal to zero, net moment is equal to zero. But when we've got this particle or concurrent force system, there's no moments. So if there's no moments in the first place, this equation over here is just going to be 0 is equal to 0. So it's not really a useful equation. What we're going to use instead for this system is just the sum of the forces is going to be equal to 0. And so with particles in equilibrium, we've only got half of the equilibrium equations to work with. So these are also vector equations we're going to be working with. So sum of forces equals 0. You'll notice it's bold, and that means it's a vector. And so when we have this, it means it has a magnitude and a direction. So each of the force vectors has some sort of strength. Say this would be 5 pounds pushing down, 4 pounds over here, 3 pounds over here. But we can't just add up those numbers because they've got different directions. So this one right in the middle is just horizontal, and these two over here, they're at angles. And so we need to take into account that direction. And so solving vector equations, we're going to break everything down into components. And there is a geometric way of doing this, but we're going to kind of skip over that. We're going to go with the algebraic way. So we need to break the vectors down into components, and what that means is each of these vectors has a part of the vector that goes horizontally and a part of the vector that's going to go vertically. And we're going to separate those into the vertical and horizontal parts to solve this. So we're going to solve each of these component equations separately. And so for a 2D problem, we've got the sum of forces equal to 0, and we're going to separate that into horizontal, which we usually call x, and vertical, which we usually call y. And so this one equation kind of splits into two equations. And for 3D problems, we actually have three separate equations. So sum of forces equals 0, splits into x, y, and z. And x is going to be back and forth, y is going to be vertical, and then z is going to be into and away from the person. So kind of the overall process, we're going from just a problem setup, an actual physical system, to solving these equilibrium equations. First thing we do is we're always going to draw that free body diagram. So here we've got a barrel sitting inside of an L-shaped bracket, and we're going to draw the free body diagram, which means we remove everything in the background. So we're analyzing this barrel, take away that L-shaped bracket, but we also add in all the forces acting on the object. So the barrel is going to have some sort of weight. I'm going to call that FA, and it's going to have two normal forces. So FB and FC are the force of the L-shaped bracket acting on the barrel itself. So now that we've got these forces, we've got our free body diagram. Next, we're going to break the vectors down into components. So FA is already kind of in the Y component, it's just a vertical force, but FB and FC, those have horizontal and vertical components. And so we're going to take away those vectors and kind of replace them with the vertical and horizontal components. So if we've got some angles, we have the original magnitude FB and FC. We've got some angle theta and phi right here. What we're going to be left with is the vertical component is going to be sine theta times FB, or sine phi times FC. And the horizontal components are going to be cosine theta times FB, or cosine phi times FC. So this is the horizontal and vertical components. Now we've got it all separated out into those two separate categories. There's no diagonal vectors at this point. Next, we're going to sum all the components in each of the directions. So starting with the x direction, it's going to be horizontal. We've got cosine theta FB, that's this vector right here, minus cosine phi FC. And so this is going in the negative direction, so it's going to be negative, and this is the magnitude of cosine phi FC. And so those two things added together, that's all of the horizontal components, are going to be equal to 0. That's what our equilibrium equations tell us. We can do the same thing with the vertical components. So FA is negative, it's going down. So negative FA plus sine theta FB, that's this force right here, that's going to go up, so it's positive. Sine phi FC, that's the vertical component over here. Those are the three vertical components. I add those together, and these are going to be equal to 0. That's what I know for my equilibrium equation. And so here, I've got my equations. So the next step is simply to solve the equations for the unknowns. So what would we know? What don't we know? Chances are, if we've got this barrel, maybe we know the weight. That would be FA. Maybe we know these angles. If we know the geometry of that bracket, I might know theta and phi. But I might not know the normal forces. So FB shows up here and here, and FC shows up here and here. If I've got two equations, I can solve for two of these unknowns. Say FB and FC. At this point, it's all algebra. You've got two equations. You write in the numbers you know, such as FA or the angles theta and phi, and you solve for those unknowns. So with that, that's all you really need to know for solving the equilibrium equations, for a particle at least. So that's all we have for the video today. Thank you for watching, and I hope to see you again.